Hello, my name is Riley Pointer, and this is my lab report for Physics Lab 3, Black Hole. The purpose of this lab was to find the mass of black hole by analyzing the orbit a star takes around it, and then use that mass to determine the initial velocity a ship must have to escape the black hole's gravitational force. So during this experiment, several physics equations came into play, such as universal gravitation and the magnitude of universal gravitation, Newton's second law slash the momentum principle, and the parallel and perpendicular components of the net force. So the reason some assumptions have been made during this equation. For example, as the experiment occurs in space, the only force present is gravity, as there's no air resistance since there's no atmosphere. Additionally, as universal gravitation is non-constant, the average velocity will be replaced with the final velocity. Next, if the parallel component of the net force is in the same direction as motion, the object is assumed to be accelerating. And finally, it's assumed that changing the perpendicular component of net force will change the direction of motion. So for this experiment, everything was done in Glow script. For the first part, the VPython model had a ball, which modeled the star, travel in motion around a stationary black circle to model the black hole. For the second part, a purple ball, representing the spaceship, departed from a cyan ball, which represented the planet, and orbited the black hole. So the first part of the experiment, as stated earlier, was to find the mass of the black hole. So the mass is found to be about 1.5 times 10 to the 34 kilograms, with the net force being 9.5 times 10 to the 28 newtons, the parallel component being 9.5 times 10 to the 28, and the perpendicular component being 9.12 times 10 to the 28 newtons. So part two explored the question of what if we want to use the black hole's or gravitational pull to essentially slingshot the ship. So it was found that the initial speed would have to be negative 7.41 times 10 to the 6 meters per second for the x component, 9.72 times 10 to the 6 for the y component. Additionally, it was found that on the planet and the ship, the black hole had the largest impact on its forces, with the net force for the planet being largely determined by the black hole and being 8.04 times 10 to the 32 newtons in the x component and 3.68 times 10 to the 32 in the y component. And on the ship, the net force was once again determined by the black hole, that being 8.68 times 10 to the 14 newtons in the x and 1.13 times 10 to the 14 in the y. So in this experiment, there were a couple of sources of error. First off, running it longer in Glow script could help improve the accuracy of the results. And additionally, improper coding, for example, when determining the mass of the black hole and other independent variables, would have impacted forces that are dependent on those variables. So what does this all mean? So first, the parallel component of net force is the net force component parallel to the direction of motion. The perpendicular component is the net force component perpendicular to the direction of motion. Net force is equal to the change in momentum over change in time, or mass times acceleration, or the sum of all forces acting on the system. The rate of change of momentum is equal to final momentum minus initial momentum over delta t, and momentum is mass divided by velocity. So the final question was a derivative of part two, saying what if instead of wanting to slingshot ourselves, we wanted to orbit the black hole? So it's found that the initial velocity of the ship would need to be 4.08 times 10 to the 6 meters per second with the initial in the x direction and 9.86 times 10 to the 6 in the y direction. And it was also found that the ship orbits the black hole at about 9.1916 times 10 to the 6 meters per second.